Hello everyone, my name is Tushar Rana and I am from IIIT Sricity and I am a second year undergraduate student doing CSE from BTech. Okay, so today our chapter is coordination compound. It is a chapter of our inorganic chemistry. Okay, let me take out my drawer first. Okay, we will study this chapter coordination compound. Okay, it is a very important chapter with respect to the JEE means and other competitive examination also. Okay, so just mark the heading coordination compounds. Okay, what about this chapter? This chapter involves very complex compounds formation and study of their energy and different structures, different isomers, different nomenclatures. But you may have studied about the IUPAC nomenclature in for simple compounds also. But here we will have the compounds very much complex. It will be something ionic and more dense like dimer, diene, and many more. Okay, let's get started. So in the first half, we will study some of the theory part, and then we will try out some questions which were asked in the JEE mains. Okay. Complex compounds are a special class of compounds in which the metal atoms or ions are bound to a number of anions or neutral molecules. Okay, so what this is saying, the complex compounds. In complex compound, there are many metals. Okay, if we take an example of metal, okay, and it is connected to many anions, any neutral molecules, and many more. Okay, so we can't predict that if one is cation, then other is anion. It may have both. Okay, so let's take it consists of cationic and anionic part both also. So for example, here it is given if it is a metal, then this L, it is anion. This is metal. Okay, and some are the this L can be anion also and neutral molecule also. Okay, so it is a dative coordinate covalent bond between them. This is half one and this one half uh, formed by the mutual interaction of the both molecules, that is anion or neutral molecule or this metal. Okay, in modern terminology these compounds are called coordination compounds. Okay, because both the different type of molecules coordinate with each other to form this type of bonds. Okay, coordination compounds or complex compounds are a type of addition compounds. Okay, now let's move on to a more deeper part. On the basis of nature, addition or molecular compounds are divided into two categories. Okay, we divide here molecular compounds into two categories, that are double salts and coordination compounds. Okay, based on the name nomenclature name also, you may have made an idea what a double salt and coordination compound, or also you may have heard this term in previous classes also. Okay, so let's okay, I will zoom a little bit so it may be visible to all of you. Okay, now I think it is more than visible. Okay, now talking about double salt, these exist only in solid state and dissociate into constituent species in their solution. Okay, so based on the definition, you understood what it is written. Now moving on to coordination compound, they retain their identity in solid as well as in solution state. Okay, so it is saying that if we have a salt, like we simply take a salt of NaCl. Okay, if we okay, this exists in a solid state, you know, NaCl, that simple salt. Okay, now when will it will if we mix it into the water, okay, it will dissociate into Na plus and Cl minus, and it will dissociate into constituent species. But for this coordination compound, there are some compounds like this FeSO4, NH4, SO4 whole dose 6H24. Okay, this is a type of double salt. Okay, it will dissociate into its constituent ions. But here, if we take the example of K4 FeCN6, okay, so it is K4 and FeCN6. Okay, so K4 will be dissociated, but the FeCN6 will, it is a whole compound, so it will not dissociate. So it remains solid as well as in the solution state. They lose their identity in dissolved state, true. they do not. Okay, their properties are essentially same as those of constituent species. Their properties are different from those of their constituent species. See here, we have given an example also. Firstly, I mark here coordination compound. Okay, I'm taking this example more seriously because we will discuss this coordination compound only in this chapter. Okay, so for example, K4 FeCN6. Okay, it is a very important compound also. You also have to learn this. Okay, in the nomenclature part, you are required to find what is the nomenclature of this compound. Okay, there will be separate terms. Okay, does not show the test of Fe+2 and Cn minus ion. Okay, that I was trying to say, because if it will dissociate now, it will dissociate like this: 4 times of K plus FeCN6. Okay, this whole part is an ion part. Okay, so this part will not dissociate. Okay, so we can't be able to find Fe+2 and Cn minus ion. Okay, so that it was same because it does not dissociate neutron, its constituent particles. Okay, now talking about the last example, last point, in double salts, the metal atom or ion exhibit normal valency. Okay, in coordination compound, the number negative ions or molecules surrounding the central metal atom is beyond its normal valency. Okay, that I was trying to say, because this compounds contains many anions form, but this is a complex compound separating that cation part, and this whole part is an anion part. So we will not able to find that different valency. Okay. Now, okay, I have taken this example because it is also important, like more salt, FeSO4, NH4 whole twice, SO4 dot 6H2. It is a tripod double salt. Okay, you just revise that. Now, double salt and coordination compound. Okay, an aqueous solution of potassium will give the test of K plus, aluminum plus 3, and SO4 minus 2. Okay, this compound K2SO4 dot Al2SO4 whole thrice dot 24H2. See here, it is here there is not that type of that bracket type of complex compound. So it is truly visible that it is a type of double salt, and its name is potassium. Okay, so we will we will add it to water and dissociate. It will give the test of K plus, aluminum plus 3, as 4 2 minus, and water remains same. Okay. Now, on the other hand, coordination compounds are molecular compounds that retain their identity even when dissolved in water. Okay, so it is saying that coordination compounds are molecular compounds that retain their identity. Okay, on dissolving into water, they retain their same identity as previous in the compounds. Okay, now when potassium ferrocyanide, that is K4FeCN6, I told you just try to find its name because it is a very important compound. Okay, its name is potassium ferrocyanide, and if Fe plus 3 there comes, then potassium ferrocyanide, and many more compounds are there. Okay, it's dissolved in water. It does not give the usual test of Fe+2 and Cn-1. I told you the reason. Okay, indicating that FeCN6 minus 4 does not dissociate into Fe+2 and Cn-. Okay, that I was trying to say. See, K4 FeCN6 dissociate into 4 times of K plus and Fe4CN minus. Okay, here I didn't mention the minus sign. Okay, see, but it does not dissociate into this. So that I was trying to say. Now, complexes compounds. Okay, we have seen the coordination compound. Now, this complexes compounds is generally this FeCN6. Okay, minus 4. If we doesn't see that one, this is a complex compound. Complex compound. Okay. So, what are these complex compounds? Compounds that have complex ions are called complex compounds. Okay, as the central metal ion is in the complex compound, ion forms a dative or coordinate covalent bonds with the species surrounding it. Complex ions are also known as coordinate ions, and hence the corresponding compounds are known as coordinate compounds. Okay, see in this diagram we have a metal ion. For that example, here we take this K is a metal ion, and this FeCN6. If I will make a diagram of this like this, like if we make a diagram like this, okay, and if we FeCN6, okay, so this bond is the bond formed by the both the coordination chemistry. Okay, so it is trying to say like that. Now we move on to the Werner's theory. If you have read this chapter ever, so you may have heard about this term Warner's, because most of the question comes from this part only. Okay, and the other concepts are also cleared from this theory if you know what it is trying to say. Now, forget this. Okay, on the our chemist Alfred Bernera Swiss put forward a theory to explain the formation of complex compound, how the complex compounds are formed. Okay, so it is named as Werner's theory by the name of scientist. All you know. Now, it was the first successful explanation, became famous as the coordination theory of complex compounds, which is also known as Werner's theory. Okay, just an intro part. Now, what is the main thinking part, main explanation given from this oneness theory? There were certain postulates regarding the oneness theory. Okay, first one. The central metal atom or ion in a coordination compound exhibit two types of valency. Okay, primary and secondary. So what I want to say is that, like, if okay, let's just read it. Then I will explain. Second, the primary valencies are ionizable and correspond to the number of charge on the complex ion. Okay. And primary valency apply equally well to simple salts to complexes and are satisfied by negative ions. Okay. So there, okay, let's take this example only. So we have this cobalt. Okay. Cobalt and the charges coming on the cobalt is cobalt plus 3. Okay. So see, there is a name given for this formula CuCl3 dot 6 NH3. Okay, if we move this part apart, okay, because this is the remaining part, but cobalt plus 3, if we want to make it stabilize, then it will come Cl minus 3 minus 1, 3 part. Okay, Co plus 3. So that Cl minus 3 are contributing to cobalt plus 3 ions. That is our first type of valency, that is known as primary valency. Okay, just you need to focus on this. Okay, same color, I took a red color else. Okay, see, this is the primary valency. What is the primary valency? Primary valency is generally the oxidation number, that is oxidation state, which you generally find in the redox reaction chapter many times. So I think that you are able to find the oxidation number. Okay, so for this cobalt, this compound CuCl3 NH3, the oxidation state of cobalt is plus 3, and that is our primary valency. Now, what is the secondary valency? Secondary valency corresponds to the valencies that a metal ion towards neutral molecules negative ions in the formation of its compound. Okay, so it is trying to say that the secondary valency can be computed from the number of compounds which are attached to it that can may contain negative ions or may contain some of the neutral ions too. Okay, I will teach with this example also, just a little bit more theory. Second part. Secondary valency are directional, and so a complex has a particular shape. Okay, so this point you must mention particular shape, and secondary valency are directional. Okay, the number and the arrangement of ligands in this space determines. Okay, I will talk to you about ligands later. In the space determines the stereochemistry of. Okay, you know about stereochemistry of a complex in the obviously second part. Okay, you have heard about this stuff. Now, what I was trying to say, the secondary valency. Okay, I will write here also. Primary valency. What is primary valency? It is just oxidation number. Okay, and secondary valency, you can just say number of neutral or negative ions attached to that metal ion. For this example, I am to say, okay, like this. For this cobalt plus 3, we have Cl. Okay, it is the part of this compound only. But we apart from this, we have neutral molecule NH3, 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 NH3. So we have 6 NH3. Okay, so this is the secondary valency only. Okay, so in this type, you need to understand what is that, and it is generally known as coordination number. Okay, okay, coordination number. So secondary valency is equals to shit. Okay, is equals to coordination number, and primary valency is equals to oxidation number. So you can make relation like that. Now, application of Werner's theory. What to do with this Werner's theory? Okay, let's say applications of Werner's theory. Okay. So where to apply this one theory? Basically, if you want to find a certain nomenclature or certain structure of a compound, we will read it. Okay. Mostly in the case of salt formation, we use that. Now, here CuCl3.6NH3 giving you 3 times of AgCl. Okay. If it is written 3 times of AgCl, so it means that it is dissociating its all 3 chlorine ions. Okay. So here 3 times of AgCl giving you CO NH3 whole thrice, NH3 it is this one, and whole 6 part, and coming with the Cl3 molecule. Okay, so 3 chloride ion will be dissociated into water. Now, if we get COCl3.5 NH3 and we get 2 AgCl, then it means that we only get the 2 Cl ions that remains in the compound only, and 1 Cl ions get dissociated. Okay, so see. That is CO and H3 whole thrice, and this is 5 part, okay, and Cl2, so 2 chloride ions. So it can be asked in the question, like if you have given this type of compound and you may have given the product, so they will ask how much chlorine minus ion that is dissociated into water, okay, like that question. Now COCl3.4 NH3, okay, you may also, and giving only 1 AgCl. So if 1 AgCl giving means 1 Cl ion is dissociated, okay, 1 Cl ion is dissociated, it means that the Cl2 will be left here only, okay, so like that. Now, if COCl3.3 NH2 and no AgCl means no Cl dissociated from that compound, and the whole compound is there readily available, CONH3 whole thrice 3 and Cl3 whole, so no chloride ion, it means that no precipitate formation, okay. So like that it can be asked in the question, okay. The thing is that don't lose this part, it is very important. Many questions are asked from this only. On hitting with HCl at 373 cobalt amine, okay, some theory part, primary valency and secondary valencies, I told you all the compound different their reactivity. Okay, now Werner's theory. Werner's theory proposed putting all molecules and ions within the sphere in the brackets and those free ions, okay, that I told. Okay, for example, this is just we have read it, COCl3 and all these forms. It is their color, that is physical properties, and ions per formula. This is 4, 3, 2, 2. Okay, you know how this ions per formula unit is formed. Okay, free Cl minus ions, that is 3, as you know that 3 AgCl, here 2, here only 1 AgCl, here also 1 AgCl. Okay, so this is the formula after the formation of that AgCl. Okay, and there comes a, and this is the compound, this is the same compound. Okay, this is the same compound, this is the same ionic unit, and this is the same Cl minus ion dissociated, but we get a different two structures, that is one cis and one transform, because we will read about isomerism also in the later. Now, what are ligands? I told you I will talk about ligands later. Now, let's see. Ligands. The molecule or ions which are coordinated to the metal atom or ions. Okay, that I told now. Like this is cobalt. Okay, this is our metal. Okay, but the molecules which are coordinated, like I tell NH3 6 times. Okay, this is our ligands. Okay, like for example, K4FeCN6, the 6 cyanide group. This 6 cyanide group coordinated with Fe+2 are the ligand. Okay, we didn't if in the coordination compound we get a compound, then we didn't take the metal ion or that is outside, we just take the metal ion which is formed in the complex compound. Okay, that is Fe. Okay, this one atom, this is the our metal atom ion. Okay, and these are the ligands. Now, ligand can be negative ions, positive ions, or neutral molecules. I told you in the earlier section only. Now, ligand are Lewis bases. Okay, this is also an part where you can identify if your compound is a ligand, or sorry, if your molecule is ligand or that metal ion. Okay. Now, central metal atom or Lewis acid. Okay, that central metal atom or ion is Lewis acid. Tit for tat like that. This is a Lewis acid, and these are Lewis base, Lewis acid, and this ligand I take, this is ligand. Okay, that is known as Lewis base. Now, There are many types of ligands. We will discuss two to three types. First one is monodentate ligand and second one is polydentate ligand. Okay, and there comes one also ambidentate ligand. If a ligand has two or more donor atoms, complex is formed only one donor atom is attached to that metal atom. That is our ambidentate ligand. Like this, MNO. Okay, okay. Like this is NO2. This is also NO2, and it is coordinated to the metal atom ion. But the orientation of this connection is different, like this nitrito ion, because N is connected to M. Okay, it is a yellow complex, and but this nitrito is connected to the O, but this O is also connected to the other O. But here we get a band structure, but here get a linear structure. Okay, so it is a red complex. Also, on depending upon the orienticity of the connection with the metal ion of the ligand, we get the different complex compounds. Okay, now talking about monodentate ligand, here we only have one donor atom or one point of attachment. Okay, simply this one point, like this oxygen, and this is metal atom. Now talking about polydentate ligand, we may have more than one donor atom, like this. Oxygen from here also can donate, and from here also it can be donated. Okay, like here to here to here. These all are bidentate ligand. Okay, this, 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 and most common is that in ethylene diamine. You may have heard about this term also. And here also come acetinoate ACAC. Okay, just learn this compounds. Okay. Now, coordination number, I also discussed about this. The number of ligand atoms bonded directly to the central atom are called as coordination number. For CONH3 also try 6. This is 2. This is EN3. Why it comes 6? Because EN contains two type. EN is a type of dimer. Okay, like what I am trying to say. See here. This is EN. This is one compound. This is one compound. Okay, so it can be connected in these two ways. Okay, so there are two donor atoms and there are three types, 3 into En. So 3 into 2 is equals to C. So that's why it is coordination number equals to 6. Ligand equals to 3 to 6. Okay. Now, geometry is related to the coordination number 2. Like if it is there metal atom ion and we have a coordination number 2, so we can simply connect by linear structure connecting both 180 degrees. Now for tetrahedral, you may have heard about this, and there comes many structures like square planar and many more. You have heard about that. Now, if 5 trigonal pyramidal, T-shaped, square pyramidal, you have heard also that. Coordination number 6, that octahedral, okay, square pyramidal, planar, okay, like that. Now we will talk about that in later part. Now let's see the complex ion. This is the given some complex ions formation. Like if we have a compound FeH2O 3 plus, so see, we can connect the H2O in the this direction. It is completely our octahedral. Okay, so and the 3 positive charge comes on the um, that complex ion. For this AlF6 and CuNH3 and CuNH3 whole you can find. Now charge on the complex ion, I will not study talk about that. Just see, you also know how to find. There is the -4, okay, equals to -4 plus 2, that is Fe plus 2 charge, and 6 times of Cn minus 1. Then you can check or you can find from this formula. Now this is the important some part. Effective atomic number. What is effective atomic number? Okay, you have to learn this. Okay, just learn. Effective atomic number is Z minus X plus Y. Z is the atomic number of the metal, that is of the complex compound. X is the number of electrons lost during see, you have to learn the terminology. Number of electrons lost during the formation of that metal ion from its atom, and number of electrons donated by the ligand. Okay, so I think it is clear now. You just need to number of electron lost, number of electrons donated. Okay, you need to see this. Like for example, we have given FeCN6 minus 4 oxidation state, it can come equals to +2 on U -4, and equating the Fe oxidation state comes +2. Okay, Cn is -1, and the Z is 26. Okay, now 26 is the Z. Okay, how many number of electrons are lost due to that oxidation state? That is R X. X is basically nothing but oxidation state, and that's 6. Okay, the 6 is the coordination number, you can say coordination number into twice. Okay, because it is a number of electrons donated by the ligand. Okay, so it will donate from the both side. Okay, like that, z minus x plus y. Now you may find the en, and you may also need the en value later. Okay, now what is the nomenclature writing? Okay, we came to the part of nomenclature. Okay, huh. Now if we have given a compound and it is asked to write the nomenclature naming of that compound, that is IUPAC naming, like basically. Okay, nomenclature of compound, but it is not compound, simple compound, it is complex. That is written in that box formation. Okay, the formula of the cation, whether it is simple or complex, is written first. Okay, so firstly you have to write the name of that cation part only. Okay, like if it comes Na4, so it is our cation part, so we have to write first sodium only. Okay, after that only we will jump on to the anion part, whether it is complex or not complex. Okay, now I will write here first cation name written first, irrespective of compound type. Okay, whether it can be complex or simple also. Whether a coordination sphere, the metal atom as well as the ligand are listed without any space between them. Okay, this is also no space there between them. Okay, so you just need to check that also. Now, if in the ionic coordination compound, the cation is named first and the separated by a space from the anion. Okay, now what we will write like that, like this cation and potassium, and Cn comes 6 times, so hexa. Okay, and for different coordination, sorry, ligand, we have different names. Like for H2O we have hydro. Okay, now for Cn it is cyano. Okay, like that. So you may also check it out. Hexa, cyano, and Fe, we will write that in Roman numbers, that is Roman followed by Roman numbers, and it is ferret. Okay, so this is ferret separated by some space. Okay, so that is a nomenclature. In the coordination entity, is there either neutral or cationic? Okay, you can see that suffix 8, we write that ferret. Similarly, solium triamino trichloroplatinate. This 8 is that suffix that comes at the end, and this is our Roman number, that is our oxidation state. Okay, there are such a certain LiLH4, lithium hydroaluminate, Na3CO, NO2 whole 26, sodium hexanitro, and cobaltate. Okay, all comes with 8, 8, 8, Roman number, Roman number, Roman numbers. Okay, and the first part is the cation part only. Okay, so you can check that. Now, let's move on to the isomerism part. I will take another page freshly. Isomerism in coordination compounds. Okay, so what does it mean by that? So if we will write the structural formula for, sorry, if we have given a compound and if it is asked to write structure of that compound, then it is not true, it is not there that it will form only one structure. There may be many structures formed from that compound. Okay, depending upon the orientation of the ligand. Okay, number of donor atoms, maybe there comes some part of amidated ligands also. Okay, let's say in isomerism of that coordination compound, we are dividing that isomerism into two parts. First are stereoisomer and second one is structural isomerism. You all know what are stereoisomerism and structural isomerism, so no debate on that. Okay, so stereoisomerism consists of geometrical isomerism and optical isomerism. You also heard about these terms. Okay, now, we will discuss about this too in stereoisomerism, and after that we will discuss about the structural isomerism. Structural isomerism generally consists of that first linkage isomerism, second one is ionization isomerism, third one is that coordination isomerism, And fourth one is that solvent, or basically more we call as hydrate isomerism. Okay, so these are the six types of isomerism we will study. Now let's see on the geometrical isomerism. Okay, six types of okay, six types of isomerism. Okay, so first one is Ma2B2. Ma2B2 means if you have a structure like M and there are two types of ligand. Okay, A, B, B. Okay, A and B both are twice. Okay, so we can connect in like this way and this way. We can't do other than this way, like, because what, if you do any certain manipulation, then it will come same as, like, if we do like this. Okay, and we connected M A this way. Okay, if you try to say that let's connect A here only. Okay, and here B and here B. Okay, it is different from this structure, but if you will see, if you will rotate like this one now, it is same as this one. And for that also case, you can check. Okay, so we will get only two structure, that is cis and trans. Okay, now getting, so here we can two isomerism structure we can say. For platinum, for this case, like platinum NH3 NH3 ClCl ClCl NH3 NH3. Okay, same structure, that is trans and cis. Okay, now if we have a ligand orientation like this, M A B C and D. Okay, and positive, like, and this is gly. Okay, this is our polydentate ligand. Okay, its name is glycno. So this PT, one part of gly, second part of gly. Okay, so only two structure possible, cis structure and trans structure. Okay, so just check it out. Now six coordination compound. Here we can find a six coordination compound like MO4B2. 4 plus 2, and this is 6 coordination number compound. Okay, and whatever that positive charge or negative charge. Okay, it also contains this cis and trans structure, and maybe many more complex compounds. Okay, now if we go on to the Ma3B3 end part, like CrCl3 NH3 whole thrice, this is A3, this is B3. Okay, so here we have some of the geometrical isomerism orientation like this: NH3 here, NH3 here, here NH3, here NH3. Okay, Cl here, Cl here, Cl here, but NH3 here. So no way that this can't be identical. Okay, not identical first. So in this way you can check it out that in different complex compounds of a complex isomerism structure in the geometrical part. Okay, now let's on to the optical isomerism. What are optical isomerism? It is the part of that stereo isomerism only. Okay, optical isomerism is like that mirror. If we uh, place our hand like this, and this will come like same, but it is a different structure on to the paper. Okay, see, if both were in on a paper, both were on a paper. Okay, so this structure and this structure are different, but both have the same image only, like this and this. Okay, now other stereoisomerism called optical isomerism or enantiomers. You may have heard about enantiomers are mirror images of each other. Okay, what are enantiomers? Mirror images of each other. Just as a right hand will not fit into a left glove, to enantiomerism cannot be superimposed on each other. Okay, so this is the important terms which differentiate what are the enantiomers and what are identical structures. Now, there are six coordination compound. Okay, okay, that is talking about six coordination number only. Like first one, MAA3 octahedral complexes containing only monodentate ligand. Okay, we will talk about monodentate ligand only. Now, MAA3 and CrCu2O4 ultra C3 minus, its name is this. Okay, now this is some of the structures which contain optical isomerism are some given examples. Okay, like CuCl, En whole twice, this is a diamine. Okay, E, that is polydentate ligand. This is also polydentate ligand. Okay, so how it comes six? This is 2, so 2 into 2, two donor parts plus Cl2, so it comes 6. Okay, like this you can see here also C2O4 minus 2 structures, so 3 into 6. So we'll talk about 6 coordination number only. Now let's see on the ionization isomerism. Okay, so first one is ionization isomerism, that is CuNH35SO4Br. Its color is red violet, and other part is NH3 5 SO4 plus Br minus. Okay, ions present in coordination compound. At the coordination, we have a coordination compound at that complex compound. We have ions too, like this Br can be separated out also, like this one. Okay, and it can be inside the structure also. So depending on that formation, we can make. Now, linkage isolation. As from the name, you can understand that there will be different linkages to each other coordination coordination compound. Okay, like this Fe. Fe is connected to Cl like this, but it is connected, but it is same. Okay, this will not create any such differences. But here NO2, like we have seen in the ambidentate ligand structure, nitrogen is connected to 2O like the symmetrical way, and one is connected to Fe. But here the NO is connected like this, and oxygen is connected to these. Okay, so it is O nitro, this is N nitro, this one is. Okay, based on this, we can differentiate into the isomerism part. Now, coordination isomerism. Coordination isomerism is there in that if we given a complex compound and there may contain more than one type of ligand. Okay, like this zinc NH3 4 hold by CuCl. Okay, there is a two type of compound. Okay, so we can interchange also like this. Cu can be separated out and zinc can be given here. So CuNH3 whole 4 and ZnCl4. So the whole complex coordination of complex compound changes. So the name will also change like this. This is tetraamine zinc, here tetraamine copper. Okay, name changes now, like here tetraamine cuprate, tetraamine zinc. Okay, so based on the coordination compound, that bracket, that structure, we can change the ligand and can form the compound. Now, moving on to the hydrate isomerism, I think it is last type of isomerism, that is our ionic isomerism. Okay, structural isomerism, because here no such chemical properties are seen. Just we are seeing the different orientation of the physical or structural orientation, like this chromium CrH2O whole 6. Okay, as it is written hydrate, so the water comes in the picture. Same molecular formula, but differ in water molecules inside and outside. Okay, if we have CrCl3.6H2, so it can be like CrCl2.H2 can come one side, and one Cl can go and dot 5H2, like this compound, and many more we can arrange. Okay, like this. Here all six H2O comes inside the complex compound, but here see, as I have written, 5H2O comes, the whole 5H2 comes, and 2Cl go outside. Okay, so it is penta aqua chloride. Okay, we write had H2O as aqua also, hexa aqua chromium 3. Okay, here 3. Okay, 2 chloro, and here is 1 2 3 4 hydro. Okay, so tetra aqua dichloro chromate, and the outside part chloride dihydrate. Okay, so we will write like that. Now, most we have studied almost all the theory. We have covered. Okay, the coordination compound is not completed yet. There comes many valence bond theory and many ligand and T2G, 2G, and many more, energy crystal field theory, and many more. Okay, we will study because it is a very big chapter. So I tried to cover in the first lecture that isomerism part and that complex compound intro and some ligand and nomenclature part. Okay, so we will see some of the PYQs related to this part only, that isomerism part and complex compound part, and in the next lecture we will study the rest part of this chapter. Okay, so let's write previous year questions. Okay, and I also want to tell you that it covers a decent amount of weightage in the full chemistry portion. I think around 5 to 8%. Okay, so it is a very big amount. Okay, because it is a very important chapter also. So let's move on to the question part. Question number 1. The primary and the secondary valence. Okay, it is come in the JEE-Main 2020. The recent means which we have given, a student has given. Okay, I have taken that questions only. So we get updated question only. Now, the primary and the secondary valency of the cobalt respectively in we have structure. Question number 1, I write it here. We have compound CO and H3 5 times, okay, and we have given Cl. Okay, there is some certain mistake I think in this compound, but it is like Cl2, I guess. Okay, like this, I guess. Now, the primary and the secondary valence of the cobalt is okay. So it is asking about the primary valence. Primary valence is just oxidation state, and secondary valence is the number of ligand connected to that group. Okay. So what is that? Okay, sorry. I guess this one is outside only. Cl3, I guess. Okay. So we can see that if it is Cl3, so it comes here +3 and it comes -1. So this +3 is that oxidation state and H3 is 0. Okay. So here cobalt +3 comes. Okay. So that can be primary valency. Okay. I guess there is a understanding. Okay. Let me cut it down and just write the correct formula. That is Cu and H3 5 Cl. I guess it was inside only. Okay. Let's see. If we have given Cu and H3, sorry for that question confusion. I have just taken it from the online. Okay. See, if it is Cl -2, okay. So if we write -2 and that comes somewhat +2, okay. So that +2 Cu minus, okay, wait. So that -+2, okay. And here that Cl -1 that goes outside that group, and you can check that oxidation state of cobalt will come +3 accordingly. Okay, and the oxidation state of that metal ion is only the primary valency, that is our oxidation state. So +3 there comes in two part, A and C. Now let's check the secondary valency. Secondary valency can be checked it out from the ligand, that is NH3. It's connected to the 5 ligand, but there comes one Cl also. You may have thinking that Cl is a negative ion, but I have said that it can be neutral also. Ligand can be neutral also, and it can be negative ion also. So this is also a type of ligand. So Cl and 5. Okay, so this comes as a 6. So A is the correct answer. Okay, secondary valency is basically number of ligands. Okay, there was a confusion in the question. Okay, I'm sorry for that. Now, let's see the question number 2. Question number 2 is saying that an ammonical metal salt solution gives a brilliant red PPT on addition of dimethyl gloxime. The metal ion is okay. You may have not about the dimethyl gloxime, but I think it is written in your NCERT book. Okay, it is generally that polyintelligent conformation. Okay, like ammonium metal salt, ammonical metal salt, that is basically NiCl2 plus, which I was talking that metals will give a solution with red PPT on addition of dimethyl gloxime. Okay, that is NH4OH plus, that is DMG, dimethyl gloxime. Okay, that is written, but it gives a red PPT. Okay, so what is the metal ion in that? Okay, so when the compound is formed from this, okay, so that DMG plus, that's the NiCl2. It is generally a solution given NiCl2. It gives a complex compound to form that red PPT, and that is a NiDMG whole twice. Okay, this is those the complex compound. So the metal ion is okay. So it is easy. You can find what was the metal ion. That is simply Ni plus 2, because this is metal ion, so it will be cation. It is minus. Okay, so Ni plus 2. So you have need to know what are the chemical reaction formation also. Let's move on to question number 3. What question number 3 is asking? Question number 3 is saying the magnetic moment of a transitional metal compound has been calculated to be 3.87 Bose magneton. Okay. The metal ion is okay. I think all know how to find the Bose magneton, that is magnetic moment. Okay. Firstly, we will say given. We have given the magnetic moment, that is mu, is basically 3.87 Bose magnet. Okay. And uh, I think you have a rough idea what we will do here. We will just apply the formula, and in the formula, we will have a term that is n is equals to number of unpaired electrons. Okay, and we will check each of that after removing that +2, that is +2 electrons from their electronic configuration, and we will get the number of electron pairs same. Then it will be our compound, desired compound. Okay, see the formula for that mu is equals to n into n plus 2. I don't think so that anyone doesn't know about this formula. And we have the value is 3.87. Okay, if we will do that n into n plus 2. So you may get a rough idea of that if we put n equals to 3. Okay, 3. And okay, you need to check this also. You can do that all square property and all that stuff. Okay, then 3 plus 2 is 5. 5 3 is 15. Okay, okay, like this. So 2 to the 4, 4 4 is the 16. Okay, 4 into 4. So 4 square equals to 16. So it may become approx about this one only, like 3.87 into 3.87. Okay, sorry, you can do that. Okay, so if n equals to 3, then it will come approximately like that only. Okay, 3.87 square mostly come approximately equals to 15. You can check also. So here we get the number of unpaired electron as 3. Okay, now let's see the electronic configuration. First one is our chromium. So if we remove 2 chromium atom, then we will get the configuration of argon 3d4. Okay, if for this Tr minus 2 plus 2, sorry, we will get the electronic configuration of uranium plus 3d2 also. Now for this vanadium plus 2, we will get argon 3d3. We have to just remember that we are removing 2 electrons from that outermost shell, and after that only we are writing that is magnesium plus 2. We will get argon 3d5. Okay, now what it is saying, the magnetic moment of transition metal has been calculated. Okay, now just check what are the number of unpaired electrons in their outermost shell. Here 3, here 2, here 4, and here 5. Okay, and we have got the unpaired number of unpaired electrons equals to 3, and here also getting 3. Okay, because D contains almost like I will write that also 1 2 3 4 5. Okay, 1 2 3. Okay, so these are the 3 unpaired electrons which are equal to this one, and it is coming to this one only. So C is our option. Okay, so like that you have to check. Now let's move on to question number 4. Question number 4 is saying number of moles of okay, let's not discuss this question now, because it is somewhat related to hybridization. We will talk about it later. Now let's see question number 5. Question number 5 is saying sum of oxidation state, that is general magnitude, and the coordination number of cobalt in. Okay, we have given the formula. Now this is the formula of this BP. Okay, not the whole. We have to make the formula, and we have to check how many, what is the oxidation state and what is the coordination number of this CO, because it is a complex compound metal ion. Okay, let's see. Sorry. Okay, so what this compound is, we have given a structure that is of Na, CO, B, P, Y, Cl4. Okay, so based on the structure, you can see that the oxidation state of cobalt is equals to +3. How it comes? See, this is Na +1. This is Cl -4. Okay, it will contribute whole. So Na +1 +4 plus this whole compound is X. Okay, so see, 1 plus X minus 4 equals to 0. You all know that oxidation. If we have to find the oxidation state, we use that formula. Now X comes equals to 3. Okay, but X contains certain also. But listen, this BPY now, this BPY oxidation state equals to 0. First, this one. This is a neutral compound. So whole charge comes on this cobalt +3 only. So the oxidation state is +3. Okay. So we get one part also. Okay. So we can set that answer 1. Okay, answer 1 no take. We just say oxidation state equals to +3. Now we need to check the coordination number. See, coordination number of cobalt is equals to +6. How it come? See, it is that much easy that okay, I think I have mistook the okay. See, this is BPY and this is Cl4. See, this one part and this one part. These are the two donor part. Okay, so this count as 1 and this count as 1, and this whole BPY count as 2. And this Cl4 will count as 4. 4 plus 2 is equals to 6. So coordination number comes 6. Now we have to write the okay. It may have come in the integer part also. So you can write integer here because nowadays the JEE-Main also includes some integer questions. Okay, 5 integers question. Earlier it was not there. So +6 plus 3 equals to 9. So 9 is the answer. Like that you have to check. Now there comes a question regarding isomerism. Let's see that. What it is saying, total number of relatively more stable isomerism possible for the octahedral. Okay, so we have given a compound and it is saying write all the possible isomerism and the more stable isomerism. More isomerism because this compound is big, so it may contain many isomerism. Okay, structure. So we just need to write the total number of more stable only. Okay, like if we have given a cis or trans, we know that the cis or trans, which one will be more stable. Now let's figure it out. This is our question number 7. Okay, so if you write the if you need to find it, so you need to make the structure. Okay, first, so like Cu is our first metal atom ion, so it will be in the like this. Okay, I will write like that, Cu. Okay, now we will connect first SCN holders because these are our that simple ligand SCN. This is simple negative one type. Now En is our a polydentate ligand. Okay, polydentate ligand means it will attach to the metal side from the two side. Okay, so En can be like this. We can connect En like this. Okay, but one other way. This one is the first type. Now second type, how we can connect, like we have connected like Cu as that. Okay, okay. Now if we connect SCN like this, okay, and we cannot change the orientation of En. First, remember that. Okay, En will connect to that like that only. But here SCN like this. But see, this is a type of ambidentate ligand too. Okay, like what I am trying to say, it can connect from that both carbon also and NCS also. Okay, so here nitrogen plays a part. Okay, here sulfur comes a part. Okay, so this type of way. So this is a second, but we can connect in one more way. Like see, I am just removing the identical part. Okay, I can connect to both sides. I can do an upside, but it will be identical only. So now let's make something different. Like if SCN is like from both end, we can make NCS also from both end now. See, NCS. Okay, and this is Cu connected with this. Okay, and En remains same. Okay, like that. Now it is connected to the both end. See, both are different structures. So mostly 3 most stable structure will be formed for this isomerism octahedral complex. Okay, so answer equals to 3. We write here only. Now, let's move on to some more questions. I think one question will be, this one will be last question. Okay. We have the question, the conductivity of a solution of a complex with the formula COCl3 NH3O4 COCl3 NH34 correspond to 1:1 electrolyte. Okay. This question is now, this question is generally Werner's theory related question. Okay, I'm marking the topic also. Now you may have idea what to do. Then the primary valency of the central atom ion. Okay, we have to just need to find the what oxidation state. Now, what is a 1:1 electrolyte? Okay, so in the 1:1 type of electrolyte, the ions have +1 and -1 charges on them. This is the main thing you need to know. Now, what can be the possible compound? See, it can be like that: CO, NH3, 4, Cl2. Here comes +1 charge. Here comes Cl -1 charge. Like this, we can connect now. If we have given Cl as a 3 part, so we can manage to get +1 like here and -1 is like here, because NH3 will contribute to what? Like this is -3, cobalt is cobalt is +3. Okay, cobalt is +3 and Cl equals to -2. Okay, so it can be Cl +1 from here. Okay, I'm just giving the answer directly, but you now have the knowledge what I am trying to say. Okay, I have written the answer only. The oxidation state is cobalt will only be oxidation state of cobalt +3 will be cobalt is equals to +3. Okay, this one is the primary balance. If it is given as a 1:1 electrolyte, so the answer comes as +3. Okay, so till that part I have completed. Okay, this spin only magnetic moment question is also of the next part, which we will study in the next lecture. Okay, so onto this we have covered the complex compound part, that is some nomenclature part and isomerism part and some more Werner's theory and that En part. Okay, and we have done certain questions also, so keep practicing. We will meet in the next part of this chapter. Till then, thank you all of you and bye bye.